You tell me.
All yours.
Okay. I'm Facundo Paris, and this talk is going to be about text classification. The reason of this talk is because we were working with a client, and the client was classifying their emails using a keyword list. And when the mail didn't match the keyword list, it went to a default category. And the issue was that this keyword list wasn't big enough, and this default category started to grow exponentially, and that leads to unhappy customers, children crying, cars with fire, all sorts of problems, the usual. So we came up with a statistical model. This is a multinomial naive-Bayes classifier, and okay, we had very good results. So okay, I will show you the model. So the overview of the talk will be I will explain the multinomial naive-Bayes classifier. I will explain this document term matrix and this TF-IDF vectorizer concept that basically helps to give different importance to words. Then I will show you some techniques to clean the data. We will discuss evaluation metrics, and then a little code example with a BBC dataset. And okay, and if you don't know this image, you have to reorganize your priorities. You have to stop this recording now and see Men in Black. So okay. Let's begin with the classifier. First, we have to know a little bit this base part. So let's begin. Let's begin with this example. This is Steve, and this is a description of Steve. This is an evidence of Steve. So Steve is a very shy and withdrawn, invariably helpful, but with very little interest in people or in the world of reality. A meek and tidy soul. He has a need for order and structure and a passion for detail. Okay. With this evidence of Steve, what would you say that Steve is more likely to be a farmer or a librarian? Please let me know what you think.
Librarian, maybe?
Librarian, yeah.
Librarian.
Yeah.
Librarian.
Or a gamer, maybe.
Okay.
Or a coder.
Yes. So most of you say librarian, and a study shows the same, that the majority pick librarian. But what happened? We have to take into account the proportion of librarians and farmers in United States or Argentina. For example, we have like 1 librarian to 20 farmers, or maybe more. And so we have to came up with a way to put all together this stereotype of Steve being a librarian that all agree, but there is a lot of farmers. So the way that you compute this and put it all together is with Bayes theorem. So when to use Bayes rule? For example, you have a hypothesis that Steve is a librarian. You observe some evidence. This is the description. And the thing that you want to know is the probability of that hypothesis given the evidence, given that you saw this evidence. This is the thing that you want to know, right? So the heart of Bayes theorem is the following. You have all the possibilities here. This is like a rectangle with 1 to 20 proportion, think like that. And from all the space possibilities, you have some of them that fit the evidence. For example, you have like 40% of librarian fit that evidence, and 10% of farmers fit that evidence. So if you want to know the probability of your hypothesis that Steve is a librarian, given the evidence, the description, that's the way that you compute that probability. Is this area divided by the sum of this and this area. So those are the ones that fit the evidence. So if you understand this, I'm very happy and we are okay. We are going to put some numbers. Please bear with me. So we have the same here. This is this posterior. This is the thing that we want to know. And the way that you calculate this is the following. This area is this area. But to obtain this area, we have to multiply the total number of people, this the whole rectangle, times the probability of your hypothesis that is Steve is a librarian. This is this rectangle, this whole rectangle, times the probability that you see the evidence given that you are that your hypothesis hold. So this is this little rectangle over here, this subset, and you have to normalize that by the sum of all the people that fit the evidence. So you have the same term plus the farmers. So the ones that you see the same evidence, but your hypothesis doesn't hold. Your hypothesis that he's not a librarian, right? So when you put this all together, you cancel out the number of people, and this is your relationship. This is the base rule, and it's very important, this rule in statistics, and it's a way to update your beliefs, because when you see another evidence, or you can update your posterior and then use this posterior as another prior, and etc. So if you understand this, we are okay. So the example, the easiest example of this multinomial naive Bayes is a May classification, but with only normal and spam categories. So, for example, you have a data set for training that you have labeled the normal and spam messages. And the thing that you want to know, or the thing that you want is a classifier capable of predicting normal and spam messages when a new mail came to the mailbox. So you have to do the following. You have to count all the words in each of the categories. For example, in normal messages, you have dear friend, so words like that, and in spam you have more like money, be your own boss, and all kind of stuff. So this is a statistical model, so you have to compute some probabilities. So, for example, the probability of see the word dear, given that is a normal message, this stick is given, means given, is 8. That is the total number of times dear occurred in normal messages, divided by 17. That is the total number of words in all the normal messages, right? So we have this first probability, and then you have to compute the same for all the words in all the categories. So here we have all the probabilities, and we will store these probabilities in this document term matrix. Each row is this is normal messages, this is spam, and we have these two probabilities that are the priors. And for example, with Steve, we have the priors with our knowledge or with our we think that he was probably a librarian. But here we have another way. We have a more realistic way to take a prior, and is by taking the total number of mails that, for example, we have eight mails normal and 4 mails spam. So the probability of a mail to be normal is 8 divided by the total number of mails, and the same for spam. So keep this in mind. We have all the probabilities, and now we have a new mail in our mailbox, and the mail says, "Dear friend." So what happened? We have to apply Bayes' theorem. So the thing that we want to know is the probability of our hypothesis to be true, given that we saw the evidence. The evidence here is the message, "Dear friend." And for example, if we compute this row, the probability of the mail to be normal, dear, that you saw the "dear friend" message evidence, is proportional to the prior probability, this we compute in the previous slide, times the probability of seeing the evidence given that you are that your hypothesis holds, right? And this probability breaks into these two probabilities. Is you have to multiply the probabilities of dear, given that you are in a normal message, times friend, given that you are in a normal message. This is one of the assumptions of the model, and this is why the model is called naive, because you can interchange these probabilities and you will obtain the same value. So that's naive, but because when you talk, it's important, the order is important, but in the numbers, it doesn't matter. And the model works really well with this assumption, so, and is easier. So, okay, when we plug all the numbers, we plug in all the numbers from the document term matrix, we obtained this value. If we do the same for the spam messages, we obtain this other value, and this number is bigger than the other, so we say that dear friend is a normal message. That's it. This is the core of the model. This is the heart of the model, and it's very simple but very powerful. Okay, so the vectorizer and the document term matrix. Instead of using the document term matrix that we computed before, there are some clever ways to do that. So you have this TF-IDF representation that basically TF-IDF stands for short-term frequency, inverse document frequency. So basically, this TF-IDF is this TF term multiplied this IDF term. This TF term is the term frequency, is the number of times a term occurs in a given document, and this IDF term is this log function that basically penalizes you if you have a word in a lot of documents and this word occurs or appears in very much, but you don't gain any information with that word. You don't obtain any information. So let me show you an example to be more clear. So, for example, we have 4 different texts that belongs to 4 different categories. So Mylenio is a website, Mylenio is cool, Lenny is, and that's like a tech message or text. Lenny is training to play soccer, this is sports. Lenny bought stock of Lenio Labs, this is like business or something, or economy, and Lenny creates a new law, that's politics. So when we apply the TF-IDF algorithm, we came up with this document-term matrix. And the thing that I want you to pay attention is the following. Here I highlight the Lenny. Lenny appears in all of these, in 3 of the 4 texts, right? So if we see the word Lenny, for example, this last sentence, Lenny creates a new law. Look at the values. The value of Lenny is smaller than law, and that's because it is repeated in the other categories. So this is the IDF term that yes appears in here. So. And also look at the Mylenio word. Mylenio is repeated twice in one of the documents, in one of the text, and it's not repeated here in the rest of the text. So Mylenio is a very good word to identify the tech category, right? Okay, so data preparation. Well, tokenization is when you separate all the words and have like each word is a token. So you have to make all lowercase, remove punctuation, remove numerical values. This maybe you have to keep it, depends on your problem. Remove common nonsensical text, and then after tokenization, this is the interesting part. You have to remove stop words. Stop words are words that have no meaning to you, like I am, things like that. And then you have this scheming and lemmatization. For example, if you have the words transporting, transportation, and etc., you pick the root of those words. You pick transport, and it will help you to enormously this step to compute the document-term matrix properly. Then you have to. It's a very good practice to create bigrams or trigrams. For example, bigrams is to pick the New York as one word. That's you choose some words that is easiest to compute them as a one. Then you have to deal with typos, and okay, that's basically the cleaning that you have to do. And the evaluation of the model, you have the accuracy and these two metrics, precision and recall. Basically, your model will output some values or some predictions. Some of them will be true positives, some of them will be false positives. Okay, basically you compute this ratio. For example, precision is the true positives divided by true positive plus false positives, and the recall is true positives divided by true positives plus false negatives. You want that both of them be near 1. If you have only one near 1 and the other is close to 0, you have problems. So, okay, just keep that in mind. And okay, we are here to the example. We have this data set of the BBC. Here we have like business, entertainment, politics, sports, and tech. We have like 500 for each one. I know. If we take a look, okay, retention shocks. Okay, yes, it's a sport. It's a sport text. Okay, so this is a very toy model classifier, but we let's take a look. So first we import the libraries and load the data. Then we have to split the training and testing set. Here, by default, there is an 80% 80% is training and 20% is testing. You can change that, but that's like common practice. And then we are using this sklearn that it has the splitting. It has the TF-IDF vectorizer. So you basically you feed the vectorizer with your training set, and okay, then you have to feed the multinomial naive Bayes model with the document term matrix. So here we feed that, and we have this. We compute this prediction with the tested and look at the accuracy and all the metrics that we talk about. So this model performs very well. This is very high numbers. In reality, maybe an 80% is very good. It depends on your data set very strongly, and if you have your labels good, that's important too. And okay, and this is the time for predictions. So I put the 4 different texts that I show you in the document term matrix slide. Sorry, and the prediction is they are correct. Millennial is tech, this is sport, this is business, and this is politics. So that's it. That's all the talk. If you have any words or comments or doubts.
Nice. Any questions for Facundo?
I talk too fast. I'm
It
sorry.
was great, Facundo. One question. Why was Mujica on the Lenny?
Why Mujica? He's a politician.
Hey, Facundo, I have a question for you. How you define the theme, the major theme of the text? Because you say something like, I look for words like transporting or something like that, and I set the theme, the principal theme as transport. How do you do that?
Oh, I didn't do that here, but we did in the production code. But there is a library that called Spacie that is very good to you take the word, and the Spacie will output the lemma, the root of that word. That's amazing.
Okay, so you provide to this library all the words that you obtain from when you clean the entire text and remove all the non-important words. Then you provide all the words that are left to the library, and that's
exactly
how you do it.
Yes, and you keep only the lemmas, and and then you compute your document term matrix with the lemmas, with the roots. Yes, I didn't do that here, but yes, it's a way to go.
Great, thank you.
And what about the bigrams? Does the library handle that?
Yes, sklearn also handle the bigrams or trigrams for you. The way that you have to go is you compute the bigrams or trigrams and then look at the accuracy. If it helps the model, keep it. If the metrics are worse, don't keep them. That's the way.
But how do you compute them? You mean if you have, for example, New York in the text, how do you know that is a bigram?
The library will take all the possibilities and count how many times appear, and it will keep only the meaningful ones. Yes.
Okay, great.
Do you want to try some text? I don't know if it's gonna work, but do you want to try some prediction? No. Something about Lenny.
I think people can put something in the chat.
Oh, sorry.
That would be easy.
I think if this doesn't work, we're in trouble. But... Okay, let's put it. Oh.
What do you expect with that, Juan? Like with the Lenny going to the moon?
I don't know.
Sports?
I don't know. Maybe. Yeah.
Politics, okay.
I don't think it will be politics.
Lenny, what do you say?
Lenny to the moon.
Lenny to the moon.
Yeah.
Business.
Business.
Hey,
Okay.
it's
yeah.
important, yes.
Yeah, because it's fighting. Yeah.
Yeah.
Nice. I have a question about like these. Like why do you choose these methods over other things that like other tools that are available to you? Like compare, like I don't know, like how big the data set is, or like
yes.
this kind of.
First, this method is surprisingly fast. It's very fast because all you have to do is compute the probabilities. And storing in a matrix is not some fancy machine learning techniques. We worked also with a support vector machine solution, and it works very well too. But basically, it was the most common thing to attack this problem of spam and normal messages, and from there you can go further. Yes, it's like the first model that you have to take into account.
Mm-hmm.
Then you can iterate. Yes, and it's very good to explain. Here I put the references. I stole a lot from these three sources. I strongly recommend this base theory video from the 3 Blue 1 Brown channel. That's an amazing channel. That's an amazing channel. Yes.
Mm-hmm. Yeah, but it's good that you also like show that you can also like don't have to use machine learning for everything. Like this works like very well, and it's a lot simpler in this case.
Yes, and the thing is that you understand what's behind, because a lot of times the machine learning algorithm is not a black box, but it's difficult to tweak some some values, and but it's easy if you understand what's behind.
Other question for Facundo? Okay, nice. So we continue in the chat for more questions then. Like we can get more phrases to fit to the algorithm.
All right.
Thanks a lot, Facundo, and thanks everybody.
Okay. Thank you to you.
Thank you.
Thank you.
Thank you.
Great talk.
Bye bye.
Thank you.
Great talk. Thank you very much.
Take care.
Guys.
Bye-bye.